Sometimes the biggest ideas come from a single spark of imagination. In this story, that spark belongs to a visionary from Iran named Mehdi Farzeh. He looked at how things move, planes, trains, and even animals, and saw a new way forward. His ideas connect three amazing machines in a very specific order. It's like building with Legos. You have to build the base before you can add the cool parts on top. The journey starts with a powerful new kind of jet engine. From there, it leads to a revolutionary aircraft that flies like a dragonfly. Finally, it all comes together in a massive multi-terrain train that could change transportation forever. This isn't just science fiction, it's a roadmap for innovation, one careful step at a time. It's about building, testing, and making sure each piece is perfect before moving on. The core of this entire project is about building things in the right sequence. You can't just jump to the end goal, that's not how engineering works. I've learned this lesson 1,000 times in the workshop. Failure to plan is a plan to fail, spectacularly. Mehdi Farzeh's vision understands this perfectly. The first piece of the puzzle is the engine. It's the powerhouse, the muscle that will make everything else possible. Without a working engine, the plane can't fly and the train can't move. It's the foundational myth we have to prove true before we can tackle the next one. So, we start small, with the most critical component, and we build from there. It's a process of discovery, of trial and error, and of making sure our foundation is rock solid. This step-by-step process is what makes building so exciting. It's about the journey, not just the destination. Each stage presents its own unique set of problems to solve. For the engine, the challenge is control. For the aircraft, it's stability without the usual parts. For the train, it's combining dozens of these systems into one massive, coordinated machine. Mehdi Farzeh's ideas challenge us to think differently about how machines are built and how they interact with the world. He's not just designing objects, he's designing a whole new ecosystem of technology where each part depends on the one that came before it. It's a beautiful, logical progression that respects the laws of physics and the rules of good engineering. So, let's dive in and explore this incredible chain of invention. We'll start with the heart of it all, a very special jet engine. We'll examine why it's so different from the engines we see on planes today. Then we'll see how that engine allows us to build an aircraft that seems to defy the conventional rules of flight. And finally, we'll connect it all to the ultimate creation, the trifibious modular millipede dragon train. It's a mouthful, I know, but trust me, it's one of the coolest concepts I've ever heard of. This is a story about how one great idea, when built upon with care and precision, can lead to something truly world-changing. Let's get building. The first piece of this epic puzzle is the Scorpion turbofan jet engine. Now, this isn't just any old jet engine. Its key feature is something called thrust vectoring. In simple terms, a normal jet engine pushes air straight out the back, creating forward thrust. Think of it as a powerful, non-stop push in one direction. The Scorpion engine, however, can change the direction of that push. It has special nozzles that can pivot and aim the jet blast up, down, left, or right. This ability to direct the engine's power is absolutely crucial. It's the difference between a simple rocket and a sophisticated machine that can maneuver with incredible precision. Getting this part right is everything. So, why is thrust vectoring so important? It's all about control. On a typical airplane, the pilot uses control surfaces like ailerons on the wings, elevators on the tail, and the rudder to steer. These are flaps that move to change how the air flows over the wings and tail, pushing the plane in the desired direction. Thrust vectoring, however, gives us another way to steer. Instead of relying on airflow over flaps, we can steer by pointing the engine's power itself. This provides a much more direct and powerful form of control, especially at low speeds where control surfaces aren't as effective. It's like having a powerful steerable fan that you can point anywhere you want to go. Building the Scorpion engine first is non-negotiable. It's the foundational technology for everything that follows. The Dragonfly jet aircraft, which we'll get to next, is designed entirely around the capabilities of this engine. Without a working, reliable, and precise thrust vectoring engine, the concept of an aircraft with no control surfaces is just a dream. It would be like trying to build a skyscraper without a solid foundation. You have to test and perfect the engine on its own, making sure it can handle the stress, respond instantly to commands, and provide stable power. Only after we've confirmed that the heart of the machine is strong can we think about building the body around it. This process is what separates real engineering from science fiction. In the workshop, we call this proof of concept. We isolate the riskiest, most important part of a build and tackle it first. For Mehdi Farzeh's vision, the Scorpion engine is that part. We need to build it, put it on a test stand, and run it through its paces. We need to see if we can control the vectoring nozzles with the speed and accuracy required for stable flight. We need to measure the thrust, the fuel consumption, and the durability. Once the engine is a known quantity, a reliable tool in our toolbox, we can confidently move on to the next, even more ambitious stage of the project. With a perfected Scorpion engine in hand, we can now build the Dragonfly jet aircraft. This is where things get really cool. The Dragonfly is designed to have absolutely no control surfaces. That means no ailerons, no elevators, and no rudder. Look at it. And you'll see a smooth, sleek body with no moving flaps on the wings or tail. So, how does it fly? It flies using the raw directed power of its Scorpion engines. Instead of pushing flaps into the wind to steer, the Dragonfly simply points its engine thrust where it needs to go. To climb, the nozzles vector the thrust slightly downward. To turn left, they push the thrust to the right. It's pure, unadulterated, power-based flight. This is why building the engine first was so critical. The entire flight model of the Dragonfly depends on the engine's ability to vector its thrust with lightning speed and pinpoint accuracy. A sophisticated flight computer would take the pilot's commands and translate them into tiny, precise adjustments of multiple Scorpion engines. This system would allow the Dragonfly to perform incredible maneuvers that are impossible for conventional aircraft. It could hover like a helicopter, slide sideways, or even fly backward. By removing the need for control surfaces, the aircraft becomes simpler in some ways. Less mechanical complexity, less drag, but it places all the burden of flight squarely on the engines. It's a radical new way of thinking about aviation. The Dragonfly jet aircraft isn't just a cool toy, it's a necessary stepping stone. It serves as the test bed for the control systems that will eventually be used in the much larger Dragon train. Building the Dragonfly allows engineers to solve the complex problem of coordinating multiple thrust vectoring engines on a single dynamic platform. It's one thing to test an engine on a static stand, but it's another thing entirely to make it work on a vehicle that's moving through the air at high speed. The Dragonfly is the perfect intermediate step. It's complex enough to test the core principles, but simple enough to be manageable before scaling up to the final massive project. Think of the Dragonfly as a single flying module of what will become the Millipede Dragon train. Each car of the train will essentially be a modified, ground-based version of the Dragonfly, using the same engine and control logic. By perfecting the Dragonfly's flight, we are simultaneously perfecting the movement and control system for each segment of the train. We learn how to manage the power, how to ensure stability, and how to make dozens of systems work together seamlessly. Every hour of flight time in the Dragonfly provides invaluable data that will make the final vision possible. Without this crucial middle step, jumping straight to the train would be an engineering nightmare. Now we arrive at the grand finale, the Triphibius Modular Millipede Dragon train. Let's break down that name. Triphibius means it can travel over 3 types of environments: land, water, and even rough, muddy terrain. Modular means it's made of many individual self-powered cars that link together, just like a Lego chain. Millipede Dragon describes its appearance: a long, segmented body that moves with a fluid, powerful grace. Each car in this train is equipped with its own Scorpion engine. The principles of thrust vectoring perfected in the Dragonfly aircraft are now applied on a massive scale. The train doesn't need wheels or tracks. It hovers just above the ground on a cushion of air generated by its engines. The true genius here is how the lessons from the Dragonfly project make this train possible. Each car of the Millipede Dragon train is like a flightless Dragonfly. Its Scorpion engine provides both lift to hover above the surface and thrust to move and steer. A central computer system coordinates the engines on every single car, allowing the entire train to move as one cohesive unit. It can snake through canyons, cross rivers, and glide over swamps with ease. This is where the modular design shines. The train can be made longer or shorter by simply adding or removing cars, depending on the mission's needs. It's a level of versatility that conventional trains bound to their tracks could never achieve. The importance of this invention is immense. Imagine a rescue vehicle that can travel over any terrain to reach a disaster zone. Think of a cargo transport system that doesn't require roads or railways, opening up remote regions of the world for development. The Millipede Dragon train represents a leap forward in logistics and transportation. It's a machine that adapts to the environment instead of forcing the environment to adapt to it. This is all possible because of the step-by-step process. First the engine, then the aircraft, and finally the train. Each stage proved the technology and refined the control systems necessary for the next. It's the ultimate payoff for all the hard work that came before. In the end, Mehdi Farzeh's vision is a powerful reminder that innovation is a journey of 1,000 steps. It's about having a big, bold dream, but also having the discipline to build it one piece at a time. From a single powerful engine comes an agile aircraft. From that aircraft's proven technology comes a revolutionary train that can go anywhere. It's a chain reaction of creativity and engineering. This is what it means to turn imagination into reality. You don't just dream up a dragon, you build it scale by scale until it's ready to change the world. And that, my friends, is the beautiful, messy, and glorious process of invention.